We have an exam scheduled for, so exam 2 is for Friday. That would be the 28th. Okay, so my first question is, a lot of people are also in dynamics, and dynamics got pushed back 2 days. How many people would like to take this test Monday instead of Friday? Nobody. Some people would, but some people would not. Okay, well, let's do this. So we'll do the test Friday, like normal. And if it works better for you to take it on Monday, just come talk to me and we can arrange that, okay? And the topics for this are going to be everything up through so topics up through pure tension and compression. I'll get a couple of simple problems up for pressure vessels. That's the last topic in pure tension and compression. Okay, and those will be assigned for today's class, and that'll be the last stuff on this exam. Okay. And then binders. Turn in with the exam. I actually, I can probably do them, at least I can do most of them while you're taking the test, and then you can get them back right after that. Yep. That's right. This is the second batch, isn't it? It's hard for me to keep track of all this. Yes, some people are done with this. Other people, if you bring it to the exam, I can do it while you're taking the test, I think. No, no, you do not. I love giving extra points, but I can't do it. That's just too far. Any other questions? All right. Anybody have any homework questions you want to see? Okay. Do you have it with you? So this is tension compression. Number 5. And you have a pin over here. Pin over here. These angles are both 40 degrees with the horizontal. There's a pin here, and then a 10,000 Newton force straight down. This distance is 0.25 meters. and so is this one. The members have a circular cross section. With a radius of 0.005 meters. 0.005, 5 millimeters. At the midpoint of the right beam, what are the stress tensors? At the top, bottom, and middle of cross section. Okay, and then well, there's no information about weights. We're supposed to neglect the weights, and so this little hat here, this extra piece, isn't doing anything in this problem. Okay, so to do this calculation, it's exactly the same problem as if this extra part wasn't there and it was just that triangle. If you have a body with pin joints and no weights, then the stresses act, or the forces, the external forces at the pins act towards each other, away from each other. There isn't going to be any force in this piece. So if we calculated the stress tensor of any point in this extra piece, it would be 0. There's just no loads in that at all. So so to do the truss part of this problem, we're just going to do a free body diagram of, I'll call this A. We're just going to do a free body diagram of the pin at A. So there's a force over here. I'll call that F1. A force over here, F2. And then there's the 10,000 Newton force down. To get, so a unit vector in this direction would be 40 to go this way, and then another 180. So what's that, 220? So this, you could think of this as Newton's second law. You have F1 times cosine and sine of 220 plus F2 times cosine and sine of negative 40 plus 0, negative 10,000 is equal to zeros. So that is negative 0.766 F1, negative 0.643 F1, and then positive 0.766 F2, negative 0.643 F2, plus 0, negative 10,000 is equal to zeros. The X equation just gives you, oh, I guess it gives you that F1 and F2 have the same force. So F1 is equal to F2. And so then you can write that as 1.286 F1 is equal to negative 10,000. So what do you get for F1? Seven what? 7.6? Negative. Okay. Okay. So now we're down to, we have these two members. We have the long one and the short one. The long one has a compression like this, 7776, and then this is what? Because, so we, yeah, but these are still negative. They're both negative before I, sorry. Okay, so 7776, and then this one is 7776. How do we know this is, how do we know it's in compression? What tells us that it's in compression? Yeah, the negatives. Because we started out by assuming that it's in tension. And so if you get negative values for those forces, it's in compression. And now we want to calculate the stress. And it says, so basically it asks this. At the midpoint of the right beam. So if we think about this part of the beam right here, okay? And then on the cross section, now, whenever you calculate stress tensors or strains, you're calculating that for a single point, okay? And that sometimes can get sort of lost in, like, you can sort of stop thinking about it that way because there are a lot of calculations we do where the stresses or strains at a bunch of different points are the same. So we'll do like one calculation that represents a whole beam or whatever. But, and really that's all I'm trying to get at with the wording of this question is like, okay, so now we're going to look at one point here, and we're going to look at three different points on the cross section at that level of the beam. Okay, one is here, one's here, and one's here. Okay, that might be a little confusing. The question might be a little confusing because you're like, well, we only learned one way to do this calculation. They're all going to, and they are all going to be the same, because in a beam in pure tension or pure compression, that's just the way it works. But the next topic we get to, we're going to see that things will be different depending on where on the cross section you're looking at, and additionally where along the length you're looking at. Okay, so I really the idea there is just to keep reminding yourself that these calculations, it represents a single point, you know, and those values can be, there's nothing to say that they won't be different at different points in the same cross section or whatever, you know. Okay, so now to calculate the stress. So if I choose, now I'm going to think about a coordinate system like this. That's not the coordinate system that we used in the truss calculation, but that's okay. You can, at different points of these stress problems, you can change the coordinate system at different points because we can always use principal stresses to come back to some sort of universal coordinate system, okay? So now I'm using this coordinate system. And the x normal stress is equal to the force, that internal force, divided by the cross-sectional area. And the cross-sectional area, it's round, so it's pi times 0.005 squared. That looks like that's going to be a pretty big number. Can someone calculate that? -9900717. Okay, so that's a huge stress. This is pascals. And that's the only direction where there's any stress. So the stress tensor is negative, all right, is 9.901 times 10 to the 8th. Yep. So maybe that's not so big. And then it asks, you know, basically for the absolute value of the shear stress, of the max shear stress. So that's going to be 0 minus negative 9.901 times 10 to the 7th divided by 2, which is 4.45 times 10 to the 7. And that's the same for all those points. But again, you know, like if it's asking for the maximum shear stress, you know, that's a different question for every point that it's asking you about on the beam. Well, it turns out the answers are all the same, but just remember that all this stuff, all of these things that you do, you calculate a stress tensor, you calculate the strain, the principal stress, the max shear stress, all that stuff that you can do is still just represents a single point, okay? In this problem, it just turns out all the points have the same answer, but it's important to keep in mind that the stress and the strain, that represents a single point. And so if you're trying to figure out if a beam is going to break, as things get more complicated than what we're looking at now, you're going to want to find, so say that you have a pretty brittle thing that you expect to fail in shear. So this is the thing that you want to look at. You're going to calculate the max shear stress for like, well, probably you'd want to calculate it as a function of x coordinate or y coordinate or whatever, but you'd want to see how that maximum shear changed as you went along. And then you'd want to find the maximum value of that. And that's the thing that you'd want to compare to, you know, the maximum shear stress you'd expect this material to be able to withstand. Because even if most of the points are good, if a small region of points loses its grip, you know, you get a fracture there, the whole thing is going to break, you know. Okay. In a way, that kind of, I think the wording of that question is a kind of a good lead into the next thing that we're going to go into. Any other problems you want to see?
Quick question.
Yeah.
For principal stresses.
Mhm.
That's just for the, if you draw a coordinate system with the principal stress tensor,
Oh.
how do you want to draw that? I get confused.
Okay. Okay. Only one step, right?
No, that's the most of them.
Like half the problem.
Oh, it does. That was kind of like the old me. I'm not as. All right. Well, yeah, I think it was like, I liked the idea until I saw how much time it took to get people comfortable with that, and it seemed kind of unnecessary for the benefit. But here's the idea. So, okay, say you get a, okay, so going on to a new one. Let's say that you have a stress tensor, or you get your principal stresses of 5, -6, 1, and the corresponding eigenvalues are, let's say, 0.866, -0.5. So those two go together, and then the other one is 0, +0.5. Let me think about this. +0.5, +0.866. This is plus or minus. I mean, the plus or minus is always implied when you get those values. And then the third one is plus or minus 0, 0, 1. Okay. And let's say, so we want to give the principal stress tensor, draw the coordinate system. Okay, well, there are a lot of possibilities for these, but they have to match each other. So the way I guess I tend to do it is I just go X, Y, Z in order. So my stress tensor would be 5, -6, 1. And then that means that this is my x-axis, y-axis, and z-axis. You just have to choose either the positive or negative version of that so that it has the requirements of a right-handed coordinate system. So so what I'm going to do, I guess, is just take the positive one for x, the positive of this for y. Cross product of the two will tell me which one of these I want for z. Yes, I was thinking about it wrong as I know. 1, 0, 0. Yes, thank you. So in our old coordinate system, I guess what I have is so in the old coordinate system, let's say we have the x-axis coming out, the y-axis up, and the z-axis to the left. Then the new coordinate system is going to be positive 0.866, negative 0.5. So it'll be this. And then positive 0.5, positive 0.866. So this. So here's, so now this is our x-axis. This is our y-axis. And our z-axis is going into the page. Because if you take the cross product, I mean, you can see it here, the right-hand rule says your thumb has to go into the page, so the z-axis has to go in.
So how the old coordinate system should publish our future thing, switch it.
Yeah, so those eigenvectors are meaningful as vectors in the old coordinate system. Okay, that's what the components mean. It means, so each one of these are components in the old coordinate system, but the components of each one represent the axis in the new coordinate system. Okay, it's the new coordinate system axes expressed in the old coordinate system. That's why I drew the old one here, so you could see how I had it oriented. You know, so if this was our original coordinate system, the red one, then I'm just going to use these components. The first vector is 0.866, negative 0.5. That's the green x, so on. Yeah. Right.
So yep. That could be any coordinate system you choose in the beginning, and then what the new one.
Yeah. Right. I just drew the old one up there so you could see what, because you need something to reference the new one too. Yeah. Yeah. There are at least 6 possible answers for each one of these. I think it is 6. There's 6 possible permutations because you can go for each, I don't know. That's my guess, 6.
So the first one is y is positive.
Mm-hmm. Yes, you're right. I did that wrong. It's too much thinking on my feet for me. Okay, let's do this again. Okay, so the x-axis, we go positive y, big positive y, little negative z. So we go way up here and then a little bit here. And then we go a little positive y, a big positive z. So now we go here. That's x, that's y, that's z. If you're trying to think this way, you can see possibly the benefit of choosing the axis order to be the one that most closely approximates your original coordinate system. So like call this your new x, and call this your new y, and call this your new z, you know? And then you'd have to, and then your stress tensor order would be this, 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 what did I say? This, 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 you know? But there's very little reason that you ever need to think this way. I mean, I think mostly it's like, it's just understanding how these tensors work, kind of, you know. It's really more of a mathematical exercise than anything useful for the engineering. But I think, I guess I do kind of think every time you remind yourself that you're looking at the stress for the same point, just in different orientations of the coordinate system, it kind of helps solidify the fact that, like, what those stress transformations are doing. You know, like it's still the same stress. It's still the same point. Still represents the same loading. You're just looking at it from a different perspective, and that's what's changing those numbers.
Will you ask us to draw the coordinate system?
Good question. No, I will not ask you to do that. But, oh, okay. No stretching. Any other questions?
So then for these principal stress problems, you don't want us to manually find principal stresses.
No,
How would you, how would you look like?
like I'll just give you, I'll give you principal values.
Spawn stuff off of it?
Yeah.
Okay.
Any other questions? Okay. Well, let me just briefly sort of introduce the next topic. So we're getting into stresses and beams. So this stuff is not going to be on exam 2. But the idea is, for example, let's say you have this beam that's connected to the ground by a hinge and a roller at the center. And let's say it has some mass, 50 kilograms, and let's say that there's a downward force of 2,000 newtons at the end. And let's say we know something about the cross section, we know the dimensions. What are the stresses in the beam? Let's say at this point A here, okay. Well, notice that where I drew that line A, that actually represents a finite area. And so an area is made up of infinitely many points. And so even specifying that we want to calculate the stresses at this like level along the beam left and right, we have to represent the stresses along the cross section in the cross section as some kinds of functions of like the y and z components. But that's what we're trying to get to, basically. Like you have, so if you have a big structure, you know, calculate the stresses so you can figure out which of these members is likely to break. Do you have to beef up the geometry of some of these members, that kind of thing. And in order to do that, there are a couple of things that we're going to have to talk about first. We're going to have to talk about internal loads and beams. And how many people here did internal loads and beams in statics? Okay, so I always redo that anyways. We'll talk about that. And then we're going to have to, okay, so, but you all did distributed loads in statics, right? Yeah. So this is for point and distributed loads. And then we're going to have to talk about the different stresses that come from the different internal loads. So we're going to have to talk about the stress tensor. So the internal loads in a beam, we can think of those as the internal tension, T, the shear force, capital V, the bending moment, M, the internal torque that I'll do as like a fancy T, and then after we've talked about internal loads, we'll talk about how to use those internal loads to calculate the stress tensor due to that internal tension, the stress tensor due to the internal shear force, the stress tensor due to the internal bending moment, and the stress tensor due to the internal torque. And then once we have all these, the total stress tensor is just going to be the sum of these, of all of these. Whoops. Okay. So the first thing we have to talk about is internal loads and beams. And the idea of internal loads and beams, I can't remember if I drew this picture earlier, but imagine taking your two hands and like bending a long, slender, stick, piece of wood. If you look at a free body diagram of that stick, you see a force from the fingers here, a force from the thumb, a force from the thumb, a force from the fingers. And so if all you had to look at, all you had to go on was the free body diagram, you would think like, well, the most likely places for this to break would be at where one of those external loads is applied. But you know from experience that that's actually not, none of those four places are where the stick is going to break. The stick is actually going to break somewhere between the two thumbs. Okay. So the fracture doesn't happen at the external loads. And so the question is kind of like, is there some way to use forces to measure where this thing is likely to break? And the way it works is at every horizontal location, material on the right side is applying loads to material on the left side. Vice versa means the same thing. We can look at either one of those sides. But the key thing isn't the force that's externally being applied. The key thing is the force that's required for one point to have applied by the surrounding materials in order to maintain static equilibrium. Okay, so if these, if the loads that are required for static equilibrium get too big, then the material on one side, lets go of the material it's connected to. And the stick breaks. So in other words, for figuring out when something's going to break, it's not really important to figure out what the external loads are, where the external loads are big. What's really important is figuring out what the loads are that the material has to apply to the adjacent material. When that gets too big, that's when the two pieces of material separate from each other. And so this is this is the internal loads, those loads that one side of the stick has to apply to the other side of the stick. Okay, so let me show you, let's just kind of reason our way through this. I'll set up the problem and I'll work on it next time. So let's say that we have a beam that's connected to the wall by a fixed joint. And at the midpoint, let's call this A. And let's say the length of the whole thing is 1 meter. And let's say that there's, let's say that there's a couple applied in that direction with a magnitude of 500 Newton meters. And let's say that there's also a force vector applied at the end of 1,000 newtons. That's a couple. So that's saying that you're twisting the end of this according to the right-hand rule, this direction. Okay. And let's say that this angle is 45 degrees. And we want to know what are the internal loads that are applied to the left half by the right half. Okay. And let's think about the free body diagram for a second, and then we'll do the calculation next time. So let's do a free body diagram of the left half. Okay, so here's the free body. Okay, here's the rest of the beam that we're not considering. Okay, that's not part of our isolated body, but that's the one that has the torque on it and the force on it. Okay. But the piece we are isolating, let's think about what loads are being applied to that. For now, I'm neglecting the weight. Well, this is a fixed joint, so what kind of loads can a fixed joint, and if you're thinking in 3D, what kind of loads can be applied to a body by a fixed joint? That's if it's in 2D, that's exactly right. This is in 3D, so there's actually 3 directions possible of force and 3 components of couple. Okay. And so we have forces this way, this way. There's potentially one out of the plane, but since there's no forces applied that way, we're not going to need to use those. So, you know, we could have like a, let's call this a Rx, Ry. Okay. Then there can be a couple component this way. I'll call that Mr for reaction moment. Okay. And then there's no need for a couple to keep it from tipping out of the page this way or into the page that way, like that fish, that trout that sings, when he comes out. It's not going to do that, right? But there is a couple here that's trying to twist it. So the wall is going to apply a torque. So I'll call that, so I'm going to put that over here. Put 2 of these on so you know it's a couple, and I'll call this TR, a reaction torque. They're different components, that's all. So yes, exactly. So this is the component of couple that's coming this way, and this is the one twisting it that way. Okay. And then what's happening on the other side? I'll go through this fast, but so we dealt with the fixed joint, but what's happening over here? Well, this edge has loads applied to it by the missing edge. And you can also think of that as a fixed joint. It's the same material. And so all those same things can still be applied. We can think of, there's a, so I'm going to call this force, I don't know, Fx. And there's vertical force that I'm going to call Fy. And there's a couple about an axis out of the page that I'm going to call M. And then there's a torque T, fancy T, like that. Okay. And so once we do the external calculations, get all these loads applied by the wall, then we'll be able to use that to calculate the internal loads at that point. Okay. And if those internal loads are too big, that means the beam breaks. So that's what we'll do next time.